Okay, so we can start now the next session, which is a keynote. We have a great keynote, a great topic for the next hour or so. It's about light fields, building the core immersive photo and video format for VR and AR. We have a presenter from Google US, Ryan Overbeck, and he's going to tell us about light fields and systems for recording, processing, and delivering high-quality light field experiences, and also tell us about light fields video compression with machine learning to be viewed on low-power devices, such as Oculus Quest. I'm very excited to hear about this topic. Ryan, welcome. Please introduce yourself, what you do at Google, and then tell us about light fields.
Hi, good morning. Thank you very much for the introduction. Yeah, so I'm Ryan. I work at Google. I lead a team that works on light fields for VR and AR. And over the past few years, we've developed a bunch of approaches to try and get light field video and photos working for VR and AR. So let me just share my screen here and get everything going. And I'm sorry I can't be there in person with everybody and meet all of you in Istanbul, but we'll make do with Zoom. So yeah, again, thank you very much. I'm really happy to be here. So as I was saying, my team and I have been let me just check. Can we see the slides okay? Are we good?
We have an animation playing, right?
Great, perfect. That's great. Yes, so we've been working on light fields and we want to create immersive photo and video experiences for virtual reality and augmented reality. So we really want to create photos and videos that you can literally step inside of and move around. So I've got some video clips playing on this slide that show some examples of our work. I really wish I could put VR headsets on everybody so you could see how immersive this is in person, but chunky Zoom streaming will have to do for now. So yeah, hopefully this gives you a sense of what we do. Now, of course, there are a broad range of immersive displays available on the market now. There are VR headsets like Oculus Quest that get you fully immersed in an environment, and there are auto stereoscopic displays, light field displays like the ones from Looking Glass Factory, and they operate kind of like a window looking into a 3D scene. And then, of course, with VR, Google's AR Core and Apple's AR Kit, people can now view immersive 3D experiences on their phones and tablets. And of course, there's several companies we all know working towards AR glasses that can overlay 3D objects onto the real world. So clearly there's a need for immersive 3D content to feed these displays. Now, currently, most of this content is synthetic. This is really because existing video game pipelines and tools already work pretty well for creating 3D assets for VR and AR. So there's immersive animated movies like Coco VR here, and video games like Half-Life Alyx. And even when you want to place quote unquote real world objects and real world scenes, people are generally using technical artists to manually hand model the content and again to be rendered in 3D engines. But I personally get especially excited about real world content. I want to be able to be inside of my favorite movie, or even better, capture moments from my life and be able to re-experience them like I'm there. Now, unfortunately, real-world immersive content is harder because it requires rethinking the entire content pipeline. In order to acquire immersive content, we need new cameras or new ways of using existing cameras. We need new ways to stream and render immersive content, and we need new algorithms for processing and compressing the content to prepare it for streaming and rendering. Now, at Google and other places, we've been interested in real-world immersive photography and videography for a long time now. And we've all tried a bunch of different approaches to try and fill in this pipeline. And now the rise of VR and AR provides a really nice opportunity to aim for deeper immersion than what's been possible before. So one thing we've tried for real-world immersive content is photogrammetry. This is used, of course, in Google Earth, like this video clip here. Now, for Google Earth to collect the imagery, they actually mount camera arrays onto the bottoms of airplanes and fly them in a broom sweep pattern. But for general photogrammetry, you can also use a regular camera and move around and take pictures from many different locations. Now, photogrammetry is great because you can go anywhere and view the model from all directions, but you tend to lose view-dependent effects like reflections that just get plastered onto the geometry. And complex geometry like trees here are really hard to model. And so even the best photogrammetry models tend to look a little bit video gamey and aren't quite like being in that real world place. Now, another approach is stereo panoramas, which are used in Google's Jump VR and VR 180 programs, and also Facebook's Surround 360. These tend to use special camera arrays too, like this GoPro Odyssey in the upper right here that has 16 GoPro action cameras in a ring. So stereo panoramas are more photorealistic than photogrammetry, but you're limited to a single viewpoint, so all you can do is rotate your view and look around that way. Also, the imagery gets warped towards the top and the bottom in order to make the stereo work in this situation, and because of these things, people sometimes feel uncomfortable or even a little sick when viewing stereo panoramas in VR. So we're interested in light fields because they offer a whole nother level of realism. They give you the full 6 degrees of freedom of movement, that's both rotation and translation, in a limited space. And they give you this full movement while maintaining photorealism. So even static scenes like this come alive with view-dependent effects like reflections on the monitors here or the transparency through the windows. Also, your movement in the light field matches your movement in the real world, so people tend to feel more comfortable when looking at them in VR. So what is a light field? Well, in order to create an immersive light field, you have to take a bunch of pictures on a surface. And in this example, we're using the surface of a sphere. Then a person wearing a VR headset can move around inside of that virtual sphere. And we use view synthesis to blend between the images in real time to make it look like you're actually there at the scene where the pictures were taken. So for example, this blue head here, the rays coming out of its headset indicate which cameras you'd need to pull from in order to generate a view from that perspective. And you can see the red head in a different location would need to draw from a different set of cameras to provide that view. So light fields have been explored for a long time now. They were introduced to computer graphics back in 1996 with 2 papers, Light Field Rendering by Lavoie and Hanrahan, and the Lumograph by Gortler and others. More recently, Lytro showed off light field video in VR with a piece called Hallelujah, but it required custom playback hardware in order to view it. And none of these techniques really meets our goal of using fast, low-cost capture rig to produce high-quality panoramic light fields, which can be displayed on consumer immersive devices. And our work targets commodity VR headsets, both PC-based and mobile, laptops, and even mobile cell phones and tablets. So for the rest of this talk, I'm going to talk about the work my team at Google is doing in this space. It follows 3 papers that we've published over the last 3 years. The first paper presents our solution to light field stills. The second takes a step towards solving light field video with much better view interpolation. And finally, we have some brand new work presenting a full solution to light field video that we're presenting at this year's SIGGRAPH conference, and I'll talk about that here some. So first, I'll talk about our work on light field stills that was published and presented at SIGGRAPH Asia in 2018 as a system for acquiring, processing, and rendering panoramic light field stills for virtual reality. And this is work that I did with Daniel Erickson, Daniel Evangelakos, Matt Farr, and Paul Debevic. So this system is an end-to-end solution that makes it possible to make light fields and also enables people to download them onto their own computer and view them in VR. And we also shared this work in the form of a demo on the Steam store called Welcome to Light Fields, where anybody can download the demo and experience our light fields with their own VR headset. So I'm going to quickly walk through the system that we built for this. And all of our light field systems follow the same basic structure. So first, we need a way to acquire the images in our light fields. And so we built two novel light field camera rigs that I'll talk more about in a bit. And for these multi-camera captures, we need to calibrate the images to determine their positions, orientations, and lens parameters. And we have to do this very precisely so that the rays through the pixels of the images line up exactly. And then we have to process the images, and we build fully cloud-based processing pipelines for this. And during processing, we usually generate a geometry for the light field. And in this work, we generate a geometry for every image in the light field, a depth map for every image. And we use this per view depth map for high quality rendering. And of course, we have to compress the light field data. And for this work, we developed a practical light field codec based on the open source VP9 video codec. And finally, we can render our fully processed light field. And for this work, we developed a novel light field rendering algorithm that uses a per view geometry and a disk-based reconstruction field. So first, I'll explain how we acquire these light fields. So as I mentioned before, to acquire an immersive light field, you need to take a bunch of pictures on the surface of a sphere. And so an early concept of this was to put a bunch of cameras on a sphere surface. But given the technology at the time, it would have required hundreds of cameras. And that wouldn't have been very portable. And that's a lot of SD cards to have to deal with. And so we decided to first focus on still scenes and use a subset of the cameras and just move them around. And so this is the first thing that we built. It's based on the GoPro Odyssey rig from Google's Jump VR program. It started as 16 GoPros tightly packed in a circle, but we stretched it out onto an arc and then put it on a motorized rotation gantry. And this is the rig in operation inside the Space Shuttle Discovery. This video is sped up a little bit. For this capture, it was set to go around in about a minute. So it took about 30 seconds to a minute to do our captures. So if you take a long exposure of what the rig looks like when it's going around, the little power indicators on the GoPros trace out the shape of what's being captured. So you can see we really do get a sphere of viewpoints this way. And this rig is really nice because it's fast enough for capturing people as long as they're willing to sit still for about 20 seconds or so. But if you have a really static scene, it's nice to get much higher image quality. And so we built a version that uses DSLR or mirrorless cameras. But now, since we only have two cameras, we actually have to have those tilt up and down somehow. And so we used an idea that came from Paul Debevic's early light stage work, where we wrap a string around the center post at the top here and let it unravel as the camera rotates, which causes the cameras to tilt. And you can see the camera in the background tilting down as the string unwinds here. And if we put an LED on each of the cameras and trace it out, you can see that it produces a relatively nicely calibrated sphere of different positions. So you can also notice that there's kind of a bright dot as it goes along. And that's because we have a mode where you can tell the rig to pause at each position. And that lets us take pictures with longer exposure, which also allows us to shoot high dynamic range images with ±2 stops at every position. And right now we tone map these images during processing to provide a higher perceived dynamic range when viewing the light field in a headset. So those are the two rigs that we built, and we use one or the other depending on the content we want to shoot. And they both collect about 1,000 to 2,000 images per light field. And so how do you render a light field with 1,000 to 2,000 images? Well, there are two big challenges to making this work. First and foremost, we want really high quality because obvious artifacts really hurt immersion in VR. And second, it's got to be fast. For rendering to the HTC Vive and Oculus Rift, we need to render stereo views at 90 Hertz. That's really fast. Fortunately, we came up with a pretty simple algorithm that does well with both. And to describe our algorithm, we're going to look at this light field, which we captured inside the Space Shuttle Discovery's flight deck. The views in this video were rendered with our renderer, and so our renderer is blending together the views from the 1,000 images that make up this light field in real time. So this is the view from just one of those images. The image is projected onto the depth map geometry that's generated in our processing pipeline. And you'll notice it looks okay towards the center, but as you go towards the edges, it gets all stretchy. It looks like what it is, a texture mapped depth map. But if you look through a small dish-shaped window in the center of the image, everything there looks okay. And that's because the viewing rays through this window are close to the rays that made the image. And so if we do this for every image in the light field, we get a small window onto every image, all of them just simple texture map depth maps. And then if we grow these disc-shaped windows so that they overlap and blend them together, we get a cohesive view of the scene. We get really high quality views with reflections and refractions, mostly without noticeable artifacts. But then how do you get this fast enough to render for VR? Well, going back to the dish-shaped window, you can see that the window only sees a small fraction of the image every render frame. It would be really expensive to have to render all of every image every frame, especially when you're talking about 1,000 or 2,000 images. So we cut up the images into tiles. We use 64 by 64 pixel tiles in this example. And this allows us to then cull away the tiles that aren't visible in each frame. And so this is what actually gets rendered. We cull away all of the other tiles on the CPU and send only the visible tiles to the GPU each frame. This tiling does place restrictions on how we compress the light field though, and I'll explain that now. So compressing the light field data in a way that's compatible with our rendering algorithm takes a little bit of work. So as I said before, our light fields take 1,000 to 2,000 images, which means uncompressed, they'd be about 4 to 8 gigabytes, which would be pretty painful to store or to download. Now, the most obvious approach would be to use motion compensated prediction, or MCP, as it's used for video compression. After all, the delta between neighboring images in a light field is pretty similar to the delta between sequential images in a video stream. However, our rendering algorithm requires random access to tiles, which video compression doesn't provide out of the box. So instead, we used an approach that was published by Zhang and Li back in 2000, where we pick a sparse subset of the images to be the references used for MCP by all the other images in the light field. And this now works because we can pre-decode all the reference images at load time and keep them in memory, and then we can decode a tile from any other image instantly. And we went ahead and implemented this approach in VP9, the open source video codec. We had to make 2 small changes to make this work. In the codec, we added random access to tiles within each image so that you could decode 1 tile at a time. And we added a way to use more reference images than the 8 that VP9 allows for standard videos. And we were able to get these changes into the new AV1 codec. It's contained in an extension called large scale tile decoding. So for compression performance, the bottom line is that for high quality with no noticeable compression artifacts, we get our light fields down by 29 to 200x. But if we aim for just good quality where some texture might get smoothed, we get up to 735x. So in order to share our results with the world, we created an application called Welcome to Light Fields. And it's freely downloadable from the Steam VR store, and it allows anybody to download and see our light fields. They just need a VR-ready Windows computer and an HTC Vive, Oculus Rift, or a Windows Mixed Reality HMD. And this work created a fair amount of buzz and even won a Lumiere Technology Award from the Advanced Imaging Society. And as part of creating the app, we went out and collected a library of panoramic light fields, which we used to stress test the algorithms. And this is one of my favorite examples. It's inside of the St. Stephen's Church in Granada Hill, California. And it's really beautiful. As you move your head side to side, you can see the sunlight peeking through the individual glass panes. And as far as I'm aware, there really is no other real world capture technology that can do this the way light fields can. And then this light field just shows how robust our system is. It's inside an Airstream trailer and there are reflections everywhere. Now we get some ghosting artifacts from trying to capture the moving rig, but even with that and all the reflective surfaces, we're still able to produce a compelling and immersive experience. And so that's our system for rendering light field stills. And after we finished that work, we set our sights on solving video. And last year we published a paper to CVPR that represented a significant breakthrough towards a solution. It's called Deep View, View Synthesis with Learned Gradient Descent. And this work was led by John Flynn in collaboration with Michael Broxton, Paul Overbeck, Matthew Duvall, Graham Fife, myself, Noah Snavely, and Richard Tucker. And so for this work, we built this relatively simple light field video prototype rig. Now, for video, we can't rely on moving cameras anymore. We need a physical camera at every image location. So it's really infeasible to create a rig with thousands of cameras like we use for our light field stills work. So we decided to just start with this small rig, which uses 16 GoPros. And we started with a planar arrangement here, which is less ideal than a spherical arrangement for making it immersive, but it simplifies the problem a little bit. So the algorithm we used for light field stills, where we use a depth map for every image, only works well if we have a relatively dense set of images. Like I said before, it was 1,000 to 2,000 images for the scenes that I showed. So for video, we're going to have many fewer cameras. It probably has to be tens of cameras or less to be really usable, which means the images need to be much further apart, which also means we need significantly better view synthesis to be able to maintain immersion in the gap between the images. And so we look to recent advancements in machine learning using neural networks to help us get there. So the system works like this. Given a sparse set of input views, we use a recently introduced method called Learned Gradient Descent to generate a multi-plane image, or MPI. And this MPI is a layered representation of the scene that enables real-time rendering to new viewpoints with standard graphics hardware. And MPIs can model complex effects, even volumetric effects like this fire that you can see here. So this multi-plane image, or MPI geometry, is really fundamental to getting our improved view synthesis. So I'm going to go over the details of this geometry real quick here. So an MPI is a layered representation. It consists of a set of planes distributed in depth, and each plane has an RGBA texture map on it. And so to render an MPI to an image at a new viewpoint, we first warp all the MPI planes, and then we render them back to front using standard alpha overblending. And so by using the partial transparency of the layers, we can now efficiently render complex scenes with high quality anti-aliased edges and complex volumetric effects. So this MPI geometry isn't a new thing. The concept was used back in the early 1900s for early Disney and other animated movies. Disney built this multi-plane camera on the left back in 1937. And it just physically positions partially transparent animation cells at different distances, and that gives you the perception of depth, like you can see in the animation on the right there. So we brought back the idea of MPIs for this work because they're a nice, simple volumetric representation that can be solved using deep neural networks. Other geometric representations tend to be much harder to learn with a deep network. So our paper shows one approach for doing this called learned gradient descent, where we use a neural network to improve the steps of a gradient descent solver. And so I'll leave it to the paper to go into the details on this. But the really important part to know about this is a deep learning approach really just makes it so that you can optimize the MPI representation by minimizing the actual render error relative to images of the scene. And this is really the key to getting high quality visual results. Most view synthesis approaches use really intelligent approaches for creating a geometry by optimizing various heuristics that you kind of assume reduce the render error. But with the deep network approach, we can directly minimize the render error. That's important. The other superpower of MPIs is that it's a very simple representation that manages to beautifully represent complex geometry, some reflections, refractions, and even volumetric effects. And I'm going to show a short video clip just showing some of the situations that this can handle. So notice the trees in this scene, which are really complicated. And this scene has some thin structures that are really hard to render. And here's a semi-transparent surfaces. And then finally, this scene has really complicated reflections. And our MPI geometry is able to capture all these effects and render them pretty easily. So yeah, using this improved representation provides dramatically better view interpolation with far fewer cameras. So we built on top of this approach to build a complete system for immersive light field video. This work is brand new. It's being published at this year's SIGGRAPH, and this right now is actually the first time we're talking about it publicly at all. My co-authors for this work are Michael Broxton, John Flynn, Daniel Erickson, Peter Hedman, Matthew Duvall, Jason Durgarian, Jay Bush, Matt Whalen, and Paul DeBevick. So we wanted to build an immersive light field video experience. So we created an immersive rig. It's this hemispherical dome in the middle here. It has 46 E4K action cameras mounted on it. They're separated by about 18 inches each, and they're all time synced to record frames within a few milliseconds of each other. So it's actually relatively inexpensive and mostly straightforward to put this rig together. The key piece is this acrylic dome, which you can get in a range of sizes from places like theplasticsguy.com for about $200. Then we use a projector to display our target camera configuration on the dome. And excuse me, we used a geodesic tessellation of the sphere for our camera configuration. And then we drilled holes at the vertices of this tessellation. And then we 3D printed out some camera mounts and mounted the cameras on the dome this way. So one of the great things about the transparency of the dome is it made it really useful as a viewfinder. So on location, you can get a sense of what the scene would look like in immersive VR when setting up the shot. So from this, we get 46 video feeds, and I'm showing one example of those feeds here. Each video is taken from a slightly different perspective, as you can see. So then we feed all the views for each video frame through our deep view network that I described a minute ago, and using our learn gradient descent approach. And so we generate an image stack shown on the right here. But rather than use multi-plane images like we did before, we project onto multi-sphere images. So each image maps to a hemispherical shell instead of a plane. These hemispherical shells wrap around the viewer, providing a fully immersive view of the scene. So here's a sweep through those layers to see what they look like. You can see that each layer is a pretty accurate slice of the scene. Now, it usually requires somewhere between 128 to 256 layers to accurately represent most scenes at high resolution. This example here, we used 160 layers. And that's a lot of images that would be pretty difficult to stream over the internet, especially as a video. So we need to compress this somehow. Fortunately, you can see that most of the layers are mostly empty, so there's a lot of opportunity for compression here. So to compress, the first thing we do is squash down to many fewer layers. To do this, we first break apart the 160 MSI images into 16 groups of 10 images. So here's one group of 10 images here. So we take this group of 10 images and we create a depth map fit to the data in those images. And we create the depth map using the same method that we use to render the MPI. We just use the alpha overblend back to front in these 10 images, but instead of blending the RGB values, we blend the layer index, which corresponds to the disparity, or 1/depth. Then we just convert the depth map into a coarse mesh. This is a very straightforward process where we just create a regular quad mesh, usually 8 by 8 pixels per quad. And we just use the depth map depths for the vertex depths. And then we slice up the quads into 2 triangles per quad, and we have our mesh. And then we need to compute the RGBA texture for the mesh. And the simplest way to do that is, again, to use the alpha overblend using the RGBA values for those 10 images. And you can just directly use the result of that to then put a texture onto the meshes. So now we have 16 layered meshes that we can render in exactly the same way as we render the 160 MSI layers with the alpha overblend. And so we've compressed by a factor of 10 while maintaining most of the quality that we get from this layered representation. And this video is switching between rendering the MSI, the multi-sphere image, and rendering the layered mesh to show that they're very close in quality. The layered mesh is a little less sharp, but it's still pretty close. Then to further compress this, we pack it all into a single texture atlas. We get rid of all the triangles with alpha close to 0 and pack the ones that remain into a single texture atlas. And then we can set the texture atlas size to fit into standard video codec sizes like 1080p, 4K, or 8K. Now, if we did this independently for every frame, the video would flicker. So to make it more temporally coherent, we break up the video into groups of pictures, or GOPs, of about 60 video frames, so a couple seconds. And then we only compute new meshes for the first frame of the GOP. And then we only let the vertices of the mesh move in depth within the GOP. So I've prepared this video to help kind of show how this works a little bit better. The upper left is the rendered result. On the right, we have the texture atlas. And you'll notice there's RGB colors on the left and white and gray levels on the right. And that's because most video codecs support only 3 channels. And so we have to store the RGB values side by side with the alpha values. The RGB is on the left and the white on the right is the alpha values. And then in the lower left, I have a visualization of the depth of just one layer from the layered mesh. You can see here it's the layer that includes the welder, the man up in the top left. So as I play this video, I apologize if it's chunky over Zoom, but hopefully you get a sense of what's going on here. The timeline at the bottom is showing when we hit a GOP boundary. So each time a number pops up, we hit a new GOP. And you can see the scene on the upper left renders normally, and the camera's moving back and forth, and there's no noticeable flickering, even at the GOP boundaries. But if you watch the atlas on the right, you can see a big step change at the beginning of each GOP. That's when a new mesh is computed. So the layout of the texture atlas changes. Now, if you watch the geometry on the lower left, within each GOP, you can see some very subtle movement, and that's just the depth of each vertex moving forward and backward in order to track the movement in the scene. And then at the beginning of each GOP, you can see some triangles getting deleted and some getting added. So we have to keep all the triangles in the GOP where the alpha is non-zero at any point within the GOP. So sometimes if you watch closely, you can see the welder moving back and forth inside the rendered triangles here. And so as long as we change the mesh layout only once per GOP every couple of seconds, this change isn't noticeable in the final render in the upper left. So as you can see, we end up with two synchronized data streams that we have to send to a client. One is the texture atlas here on the right, which we can simply encode into an MP4 file encoded with H.264, HEVC, VP9, AV1, or whatever video codec we choose. And then the geometry on the lower left, we have our own very simple streaming format where for each GOP, we encode one mesh. That mesh includes texture coordinates that look up into the texture atlas. And then we have per frame vertex displacements to move the vertices forwards and backwards to track the movement in the scene. And we quantize those to 16 bits. And then we can stream the geometry to a client one GOP at a time. So all packed together, our data rates are anywhere from about 100 megabits per second to about 300 megabits per second. So this is a great way to exercise a gigabit connection or a 5G network. And so all the examples I show here are stored right about 3240 by 5760 resolution. And this gets us really high quality, about 10 pixels per degree when viewed in the headset or on a screen. But we can also pack it into a 4K stream with a small drop in quality in order to match the client video decoder hardware. And you can also see, looking at this table, that the RGBA video texture atlas tends to dominate the data size. The geometry data tends to be significantly smaller. But so now with this, we now have a totally immersive streaming 6DoF light field video solution. So we collected a library of video clips of various scenes to test our algorithms, and I can show some of them for you now. Again, I wish we could view these in a VR headset, but hopefully this video isn't chunking too much over Zoom, but you can get a sense of what our light fields look at. So this scene I use to emphasize just how well our approach captures really complicated, thin structures. These tiny branches would be really hard for any other view synthesis approach to capture, but we get them really sharp. And I'm including a depth visualization here, which really, the branches really come out there, and you can really see that we get nicely anti-alias depth of these really difficult thin structures. And of course, to show off our ability to render volumetric effects, we have to have fire. So the transparency of the layers of our representation really captures things like fire beautifully. Now, here's some tough reflections on a car here, and they look really nice. Now, our layered mesh and multi-sphere image representations actually can't quite physically represent curved reflectors like this accurately. So the MSI geometry just isn't quite rich enough to represent it. But our deep view network does the best it can, and it's able to do quite well. And so you get a result that still looks really convincing. the reflections end up getting a little smooth, but it still looks really, really nice. In general, we see that when the MSI geometry can't fully represent the scene, it'll blur things a little bit, but relative to other effects from other approaches, a bit of blur isn't so bad. It still looks believable and maintains immersion. So here's one last result. This is a scene inside a cave at Leo Carrillo Beach in California, and there's a woman running by the camera. And this shows some fast movement near the camera as the woman and her dog run by. Now this scene is great because it highlights one of the extra difficulties we found with capturing light field video. It might be hard to see over Zoom, but as she runs by the camera, especially in the darker part of the frame, you can see that she's kind of motion blurred. Now that's normal, but with our system, she's a little extra motion blurred. The cameras are all set on auto exposure, so the ones that see more of the dark cave will use a longer exposure time, which increases the amount of motion blur. Also, the cameras are time synced, but not perfectly. They can be off by a few milliseconds. And so then our deep view algorithm tends to kind of add the motion blur from all the different cameras together, and it kind of gives you this extra motion blur effect. Excuse me, it still looks okay, but for future work, it'd be nice to try and get sharper results in cases like this. Also, if you look right as she passes right by the camera, and I'll try to pause it here as she goes by there, you can see that she kind of blends into the cave here. She's motion blurred, and the color of her hat and jacket are pretty similar to the color of the cave. And so she kind of gets blended into the cave. And if we look at the depth of this here as she runs by, let's see if I can pause it in about the same place. Let's see. There. Okay. You can see, you know, even her geometry is blended in with the background. So our deep view solver doesn't really care what depth things go at, just as long as the final rendered color looks right. So since the color of her hat and coat are so similar to the cave, she can get blended into the background here. Right, so that's our system for immersive light field video, and I've covered a lot. So to quickly recap our work, we work to solve the full pipeline of creating immersive light field experiences for VR and AR. We've developed new camera rigs to acquire light field photos and videos, and we've developed new algorithms to stream and render them. And we've developed new pipelines to process and compress our light field photos and videos. So where do we go from here? Well, our light fields focus on an experience where you can move around in about a 1 meter diameter head box. But clearly it would be nice to move around more. So we're looking at two directions that provide more freedom of movement. One is room scale light fields. We have some early experiments where we capture many light fields in a large room and blend between them to provide a seamless experience. We're also looking into object light fields. So where the cameras on our rigs currently all point inside out, but if you turn them the other way, you can get a light field of an object. And then you can move all the way around it and look at it from all directions. Also, our rigs use lots of cameras, which is a pretty big hindrance to scaling this approach. So we're looking at new ways to reduce the number. Can we maintain high quality with just 4 cameras? Or even a path to 1 camera? So recent advancements in machine learning suggest that that could be possible now. And of course, it'd be great to be able to do live streaming light fields. Our current processing pipelines tend to take about a day to process an entire video sequence. So what could we do to make this more real time? So with that, that's the end of my talk. Thank you so much for listening. Thank you for having me. So yeah, I'm happy to take any questions at this point.
Thank you, Ryan. That was an excellent talk. This is like most coolest talk I've ever seen. And thank you
you.
for giving us this excellent introduction to the basics and the challenges of light field, right? From acquisition to processing to stream and the rendering. During your talk, Ali had actually started a poll on Slido. The poll asks do head-mounted displays make you sick? And here's the outcome. 58% of the participants said no, head-mounted displays do not make them sick. However, over 1/3 or 35% of the participants responded yes. Oh, right now it has dropped to exactly 1/3. So I feel this might be a kind of a major issue with virtual reality technologies right now, which is still a high percentage of users feel uncomfortable wearing head-mounted displays. And what do you think about this issue?
Well, I mean, so there's the head-mounted displays. There's some things innate to having a head-mounted display that might make some people a little uncomfortable. Things like the amount of flicker of the display. There's also the vergence accommodation mismatch with head-mounted displays. Now, those things with current hardware are tuned to about where people think, for 90% of the people or something, things like flicker shouldn't be noticeable, but to some people it still will be. Now then, of course, I think what makes most people uncomfortable is the experience that they're looking at in VR. One thing I noticed for myself, I watch a lot of stereo panorama video. I really enjoy it. But when I switch from that to light field, I notice just how uncomfortable it makes me feel. Like it does this warping of the images that makes it feel like your eye is like concentrated at this point in the middle of your head. And when you go back to like a light field where your eyes are positioned where they should be in space, it's just much more comfortable and much more natural. So I believe, and I try to follow some of the literature here. Our group hasn't specifically done like studies, but just anecdotally, people tend to feel more comfortable with our stuff. Now, and also we're not 100% relying on VR for our use cases. We're definitely interested in AR use cases and use cases that don't require you to be fully immersed. And of course, as technology gets better, I think people will get more and more comfortable using this stuff.
Thank you. So let's next go over the questions that were asked on Slido during your talk. So these questions are ranked based on how popular they are. So the first question asks, can cell phones handle generating, encoding, decoding, and rendering of light field images in terms of power consumption and a required storage space?
So yeah, so the first piece of work I showed on light field stills, so as far as generating and encoding, currently definitely not. Currently the processing is pretty intense. We're lucky to have Google Cloud machines at our disposal, so we can send thousands of machines to process these things. And even then it takes for the light field stills, it can take several hours, or for the video stuff, it takes about a day to process one of our videos. So on a mobile device, that would probably be many years. So as far as decoding and rendering, we definitely want that to work on mobile devices. And so that was especially a focus for our video work. We really wanted the format to be simple enough to view on mobile devices. And it can. The rendering is very inexpensive. It's, you end up with a scene that's alpha blended. we usually end up with 60,000 to 100,000 triangles, which is a pretty modest triangle budget even for mobile. And then for the blending, which can be expensive, especially on mobile GPUs, with overdraw, we may have 16 layers in our final representation, but the actual average overdraw is only about 4, so which is very doable on a cell phone or tablet or mobile headset. So it's definitely, the rendering side is definitely doable. And then the decoding side, I mean, it's for the video, our video streams, we pack it into like a 4K stream, and current decoder hardware on the phones can handle that without too much difficulty. So the decoder hardware really helps us keep the power consumption and everything down. And then, as I said, in terms of storage, it's 100 megabits per second to 300 megabits per second, which is a lot, but it's becoming more manageable as gigabit internet gets out there, and hopefully 5G can help with that too.
Thank you. Then the second question asks us about the future of light field. It says, the commercial light field camera Litro is not produced anymore. You think the light field imaging will continue its way?
Well, certainly. And I mean, we're doing that. I mean, so, and we at Google, when Litro disbanded, we pulled in a lot of their people and some of their hardware. So Litro people are still helping us out inside of Google for sure. And then, one of the problems with Litro's approach, I mean, that rig that they built was the size of a minibus practically. I mean, it's as heavy as a car. So that was something we really wanted to improve on. We wanted to build rigs that are more and more practical. And still looking at like our dome rigs with 46 cameras, a lot of people look at that and say, hey, I can't use a rig with 46 cameras. But when you use it, it's actually not that bad. But active research for us is simplifying that down, getting it to fewer cameras, making it something much more manageable, so that we can provide a path to scaling this. Yeah, thank you.
Then the third question is general question. When do you think this will become a mainstream technology?
I mean, that's a tough question. So, we're doing our part. I mean, part of our hope and strategy is that by sharing our work externally as much as possible, kind of spreading the word that this is now possible to do on current devices. And it's definitely possible to build a nice light field product at this point. But at the same time, there are many things that are limiting how far you can reach with this stuff now. There just aren't, quite enough headsets out there now. So if you're aiming for VR, it's still hard to do something that will scale to the level that, like, Google tends to like things that go to billions of people, and we're just not there yet. But we understand that it's a long process. Seeding a new technology space like this is hard. Like we pushed Jump VR with the camera rig and everything like that, and seeding like a whole new ecosystem is hard work. And so we're patient. I'm hoping by sharing this work, more people out there will develop other systems that push this forward and get it to something that is ready when people want to make a scalable product with this.
Thank you. The next question is actually very relevant to the multimedia systems community. So the question is, for light field video, are there parameters such as the number of layers, the number of groups, and the mesh resolution, etc., that you can adapt based on the complexity of the scene?
Oh, absolutely, all of those things. So, like, for this work with all of our scenes, one of the things we like to to communicate is that, okay, you don't have to twiddle a bunch of knobs, you can push stuff through and you'll get good results. So that's something we focus on first. Now, when we take a scene and we want to compact it more, things like that, you can pick different numbers of layers, but depending on the scene content, if there's not a lot of depth complexity in the scene, you can get that down to like 3 or 4 layers even, especially, so right now, you know, the MSI is split just evenly. That just ended up being, we tried a bunch of things to automatically adapt layers to the content, and some with moderate success. We frankly had the most success with, you know, a technical artist just taking the scene and manually tuning the layer placement. But that would be definitely something I would love to dig into, is getting the layer placement better to match the content of the scene. And then, of course, things that you use in other video things to adapt resolution in specific places, or things like that are definitely great things to poke at. Yeah.
Thank you. And then the follow-up question, sorry, the next question is on the quality of experience. Did you study the quality of experience and the appreciation of users of the different coding approach?
Yeah, so we haven't done like a formal user study of this. I mean, it's pretty much anecdotal for us. You know, each time we improve our system, we put a lot of work into showing it to people and collecting responses. And I have noticed that especially with this kind of stuff, there's a clear point where before that people look at it and say, oh, this is nice, this is cool, and then once you push back a certain point, you get a whole different bigger reaction. And so with all of our stuff, we push very hard to get to the other side of that approach where people are really mind blown, and that's the response we generally get from this. So we haven't, you know, and as far as different ways of tuning and encoding this stuff, that's a big part of getting that big wow experience. And a big part of that is actually getting the colors right and things like that have less to do with the immersive side of things. So we put a lot of work into getting color maps for our scenes that really bring out the colors and things like that.
Thank you. And then the next one asks us about the details of your CVPR paper. Is the gradient descent referring to the network optimization while training?
Right. So yeah, I can spend a couple minutes delving deeper into that. I mean, it's a pretty, it does end up being a somewhat complicated way to generate an MPI. People have also used just feed forward deep networks, 3D with 3D convolutions in order to generate MPIs. But for our gradient descent approach has some benefits, especially like it handles better resolution than these feed forward network approaches. So the main idea is you could, and it works, you could take the MPI and just use a straight gradient descent. So you start with a bunch of pictures of the scene, and you can hold some of those pictures out and then just do a gradient descent on the MPI to match those holdout views. And that takes thousands and thousands of iterations and can take days to do that. So what we do is we take a deep network that does the actual gradient descent part. So given the derivatives and the current state of the system, it decides what the next step of the gradient descent is. And so it's able to make much bigger jumps in the gradient descent. So instead of thousands of gradient descent steps, we do 3, and you know, each step takes a huge jump. And so that deep network, in order to do so well, we train it on hundreds of scenes, hundreds of other scenes, and the network learns, you know, the basics of physical structures and things like that in order to then take the data in each gradient descent step and make that big jump. So yeah, please see the paper for more. It definitely goes into it, and in deep detail. Yeah. Any other questions? Hello, have we lost our moderator?
Oh, sorry. So
Oh, yeah.
sorry, I thought I was muted. So we're going to conclude the session with Ali's questions. Without all this gear, can you actually work from home, or do you have to move all this gear to home for work?
You mean to do our light field work? Do we need like the light field gear?
Yeah.
Yes. So especially for the cameras and everything, yeah, we have to bring those home. So we, you know, we're continually working on new rigs too, and we're developing one right now, and it's involved complicated handoffs from person to person in order to move it along the assembly line to get it constructed. The Sentinel rig, that dome rig, is in one of our team members' house, and he's still actively doing shoots just within his home and outside his home, you know, outside his front door while we're all pretty locked down. And then everything else, you know, after the rig, it's all on the network as far as processing. So we're pretty good to be from home. It's just the light field capture hardware has to be physically with you at this point.
Thank you. Can we do more questions, because we're a little late, but there are two very interesting questions following up.
Yeah, I think it's fine now. Thanks.
Okay. Yeah. So there are two really exciting questions. One is with increasing compression, there comes a point where bandwidth has to be traded off for latency. With the advent of 5G and beyond, which one do you think will be the most limiting factor in the future or near future?
Oh, that's a tough question. For me, you know, as long as we're not talking about live streaming, it's okay if there's latency, as long as there's not like a delay between video frames. So you know, if there's some latency in the connection. So for me, bandwidth is most important. I mean, the biggest thing I've noticed with all these immersive videos, including stereo panoramas and things like that, is there's a quality point where, you know, you're almost better off just viewing a flat video at some point. So it's super important with immersive things to get past that quality point, and that's, you know, getting the bandwidth up to stuff more quality into the bits is what I care most about. So that's really been my focus.
The next question on capturing. You mentioned in the talk that one camera only may be possible due to machine learning advances. As long as we're not there, how big should your rig be? How relevant is the baseline of your cameras?
Right. So the main thing that determines the size of our rigs right now is the size that you want to be able to move around inside of in your immersive experience. And we found that about 1 meter diameter hits a really nice sweet spot where you feel comfortable moving around. You don't feel like you're too confined. You can do things like turn around without fearing that you're leaving the volume and stuff like that. And also, bigger than 1 meter becomes just physically hard to deal with. So 1 meter or a little under that keeps it relatively portable and things like that. So so that's the main thing that determines how big the rig is. Now, how close the cameras are together, our current biggest concerns are, you know, so depending on the field of view of your cameras, you need a certain amount of overlap from the cameras in order to be able to capture things within the field that the cameras are looking at. So depending on field of view and how far apart the cameras are, that really determines how close something can be to the rig before you can really, capture it. So, and also in immersive experience, close stuff is really the most visceral. It really lights up your brain when you see the close stuff. So we want it close. So that kind of pushes us to get the cameras as close as they are together. Now, with current GAN research and that type of thing, algorithms are getting better and better at filling in missing information and imagining stuff that's not there, and doing it in a way that is believable. And so that's the kind of stuff that we're going to have to rely on if we want to keep pushing the cameras further apart or reduce the number of cameras in order to fill in that stuff where there's just no data. So we need something to create that data and do it in a believable way. I hope that answers your question.
Thank you. So I want to conclude this session with the question from Ali. Can I make a lightsaber with this technology?
A lightsaber? I mean, you can record. Do you mean? I wonder if you mean like make synthetic scenery and record that with this technology. Maybe, or I don't know if you're trying to think, focus the light rays together to. Yeah.
I would like to scare my wife and kids. So.
Yeah, as far as actually creating a real life lightsaber or something like that, I think we're a ways away from that. But if you want to render a lightsaber in a VR headset, I mean, absolutely, 100%.
Sounds good.
Thank you
so much,
Ryan. Excellent. So
great. Thank you everybody for having me.
That concludes our session.